the last talk of the day, it was a long day today, is by Claudio Verdun from Technische University Munich. He will talk about stable non-negative least square and overparametrized point of view. Thank you.
Thank you. So hi everyone. Yeah, I'm Claudio Verdun. I'm a PhD student at the Technical University of Munich. Yeah, and that's the topic today. So first, I would like to thank the organizers for this conference, and in particular Akron for the invitation, and also thank you for surviving until here, and also all the people who are watching from home. So okay, before we start, what should I? It's not working. Okay, this works.
Maybe because it's a Zoom, you gotta click on the window again.
Yeah, I don't know. Here? Ah, okay. Okay, here we go. So, okay, that's a joint work with two friends of mine, both postdocs in Germany, Edward and Johannes. Okay, and that's the problem. The problem is quite simple. I want to solve least squares. That's it. But I have some constraint, like all the entries should be non-negative. And well, this problem, let's say, has some interpretation, because you can say that the solution somehow tells how much each column of A contributes towards the data. It has a lot of applications and connections, for example, support vector machines, many problems related to the mixing and the convolution. And yeah, nice applications in magnetic resonance imaging, genetics, and so on. And also it's somehow the basis of like many matrix tensor, many matrix and tensor factorization problems. Okay, so let's see how to solve this problem. So the first thing, yeah, one might think, okay, we solve least squares and then we project. But then this can go very wrong, because if we solve least squares and then we have like negative entries, this will turn into 0. And I mean, I just took some numerical example from a classical paper in the field, and then like they claim, look, that's the solution. And moreover, yeah, like more than that, if all the entries are negative, you will like this will lead to the 0 solution, and maybe that's not what you're looking for. Okay, so I would say that there are like 3 families of solutions for this problem: the so-called active set methods, interior point methods, and projected gradient descent. But arguably the most famous solution is the one by Lawson and Hensel, published in their book in '74. And it's basically the one that's implemented in any language. Like when you type non-negative least squares, basically that's what's behind, which is some type of active set method. Okay. And in a nutshell, so these are Lawson and Hensel, and in a nutshell, what are the problems? The first family, I would argue, there is not much theory available for that. The second one is not scalable because you have some sort of Newton's method behind. And the third one, well, for the third one, is very hard to choose the step size, because there are many counterexamples. Let's say when you take step size from gradient descent and you try to apply in a projected gradient descent version, like they don't work. For example, this paper by Diane Fletcher shows a lot of things that can go wrong in this case. And my goal in this talk is to show how some ideas from overparametrization coming from neural networks can, yeah, solve this problem in a different way. But before, I would like to say a word from our sponsors. So I come from, let's say, compressive sensing, and yeah. So in sparse recovery, what you want to do, you want to solve this problem. So you want to recover a high dimensional vector from just a few measurements. I mean, here we are talking about non-negative vector. So, okay, positive, like, okay, non-negative vector. And there is a huge body of literature about this problem. And many algorithms for this problem, they require like parameter tuning. But then it turns out that non-negative least squares is very useful for this problem as well. So first is like tuning free, because only positivity suffices for their sparse recovery. And you have bare L infinity rates, in the sense that under the same assumptions, if you compare like coefficient by coefficient, the outcome of your algorithm and the ground truth. So if you compare non-negative least squares and the last two for this type of problems, I would say non-negative least squares has better L infinity rates. And I would say all of that started, so there are many cool papers about positive solutions of like positive sparse solutions of linear systems. So these are some of the maybe, in my opinion, the most important ones. But there is one very short paper by Simon Foucault that's basically, after I read it, I was like, cool. I mean, that's a cool problem. And it has a nice comment in this paper, kind of connecting, saying, look, this Lawson-Hanson classical algorithm is connected to orthogonal matching pursuit as well. So I read and I was like, okay, that's something I understand a little bit. So let's try to work with that. So the second goal of this talk is to say something about the positive sparse recovery case, okay? But then we need to understand the technique before. And well, the technique, I mentioned these two buzzwords like overparametrization and implicit bias. So the problem, that's also something Emily mentioned in her talk today. So we have like neural networks nowadays, and they have a lot of parameters. Like this is way larger than our data set. And it turns out like it's kind of a mystery. I don't know, but I would say it's a major like open problem in theoretical machine learning to understand why, if you apply gradient descent, yeah, you can retrieve a very nice solution that, I mean, you train in your training set and then you apply in your test set and things kind of work. So there is a lot of literature now trying to understand this problem in different scenarios, and why gradient descent is so nice for neural networks. And I mean, here are a few examples. There are many problems that can be, or there are naturally overparametrized. Okay, so yeah, linear regression, Fourier transform, linear networks, and so on. And I think that's an amazing field. There are many new interesting contributions for sure, like many more papers to come. There is already a connection to sparse recovery by using some sort of overparametrized approach. Okay, and that's what we're gonna do here. Okay, so yeah, this picture is the one you should keep in mind, more or less the same one that Emily showed. So like classical statistics would tell us that, okay, the error in the test data set would need to go up because we are like having some overfitting, but it turns out that this is not the case. So that's something we should understand. And that's one thing behind this so-called overparametrized approach. So, okay, that's our approach. We take the objective function and we just overparameterize. So instead of having one vector x n dimensional, I will have L vector x's, like x1 until xl, and this product's like entry-wise, like Hadamard product, okay? And okay, if I have one layer, like I have the standard objective function, and if I apply gradient descent, this will converge to the like standard solution. And as we saw in the beginning, well, this in general will not be positive. However, things are different if L is larger than 1. And that's precisely the content of our work. So if L is like larger or equal than 2, we are able to show that if you initialize it well, you solve non-negative least squares. And moreover, if your initialization is quite small, this also approaches the L1 minimizer, which means under certain compressive sensing standard assumptions, you are getting your sparse vector back, okay? And yeah, it was quite surprising when we ran some numerics and we observed this thing. So, okay, here's our first result. That's the overparametrized objective function. Okay, one thing is it's very important to stop now and to say something like our proof technique is based on gradient flow. So we are talking about continuous things. So, well, in theory, we would need like very, very arbitrarily small step sizes and things like that. But at least based on gradient flow, we can prove that the limit of if L is greater or equal than 2, the limit exists and lies in this S plus set, which means like the limit is a non-negative least square solution. Moreover, if the initialization, so I'm initializing this vector with like a times ones. So if a is quite small, the one norm of my solution of gradient flow is also close to the L1 minimizer among all possible non-negative least square solutions. Okay, of course, I mean, that's a theoretical thing because this depends on C, here is C, so this is also the minimizer, okay? But still, I think it's nice. So a few comments. As I said, like the limit exists, and the limit will be like under very general assumptions, like on A and Y will be the solution of the non-negative least squares problem. So moreover, the like gradient descent will solve the L1 minimization problem, and I will be able to retrieve the sparse solution if A is well behaved. So if A fulfills like the standard assumptions in compressive sensing. But well, I need to be honest, there are three things. So we don't have a convergence rate. As I said, our proof is based on gradient flow. And by no means I'm claiming that we are better than these active set methods, because these methods are really precise. Like you can open MATLAB or Python now and try, and then you'll see that it reaches very, very good precision, like in a really fast way. Also, they are not scalable, I must say. So if you try to solve non-negative least squares for a 10,000 times 10,000 system with active set methods, you'll have problems. And I would say in some communities, 10,000 times 10,000 is not a large matrix. And potentially with gradient descent, yeah, we can do these things. But by no means I'm claiming that we are better than them, okay? But we have some very nice things. So in this compressive sensing regime, so if we have things like null space property, quotient property, and so on, our method is stable. But stable in which sense? Like imagine that now I want to solve not exactly a non-negative least squares problem, but my vector is corrupted, like one or two entries are slightly negative. So if you run so what we are proving here is if you run gradient descent with this overparametrized regime, our solution, we can still bound it, and the right-hand side only depends on the sparsity of the positive part of my ground truth and the two norm of the negative part. Okay, so it's kind of stable because let's say if you have a lot of zeros and you perturb things with some zero mean noise, things can become negative, and standard non-negative least squares approaches fail completely if you have a vector that's not exactly 100% non-negative, okay? And okay, so let's see some numerics. That's the first thing we did before the theorem. So here I am in some sparse case, and now we have good news. Like since we are talking about pure gradient descent, we are not in a constrained version anymore. We can play with like different step sizes. We can do things like Nesterov and like Barzilai, Borwein step sizes, and this will work really well because we don't need to care anymore about the fact that we are just solving things in this constraint set. So here is basically the solution. We are measuring here the two norm of AX minus Y. And here, for example, is like the median over 100 runs of the number of iterations we need in order to reach relative error 10 to the minus 3. And here, relative error is really like the two norm of X minus X naught minus the ground truth. So here, I'm measuring two different things. Here's the dense case, the non-sparse case, so m equal to n equal to s equal to 50. It works. It takes a bit longer, but still works. You just need to iterate more, and this is quite fast, like in terms of running time. Moreover, there is as I said, our result is for L greater or equal than 2. So we could go for L equal to 3, L equal to 4. We can just append like vectors in this overparametrized regime. So here we are like we have the same situation as before. So S equal to 3, and we are comparing what happens to these 3 coefficients that are different from 0 when we run gradient descent with 2 layers and gradient descent with 3 layers. So you can see, I mean, we are still trying to understand that, but you can see that and first, second, and third here mean like I'm starting from the largest one. So first mean the largest coefficient different from 0. So they go down for 2 layers, they go down before compared to the 3 layers case, but then with 3 layers we are more precise, and the more layers we have, the more computational effort we have, but then we are more precise. And here's just a zoomed version, like the first 250,000 iterations of this plot here. Okay. Also, yeah, maybe that's a very misleading picture, but still I'm showing it here. The role of initialization, because I mentioned in the beginning that if the initialization is quite small, you can also reach the L1 minimizer. So here I'm trying to plot the L1 norm of the solution, and I'm comparing with like CVX solving and like non-negative least squares and basis pursuit. I mean, the 2 lines here in this example, they are together, but if the magnitude of the initialization is not so small, you cannot reach this L1 norm. Of course, you can argue that, okay, maybe it's because you need, I mean, it will take longer, or you need to change the step size. So as I said, this picture is very misleading. There are things behind it, but still, I think it's worth it to show. And now for the stability. So let's say we have a Gaussian matrix here. We have L equal to 3, and then my ground truth has also a negative part in the following way. Like, I mean, I have this parameter Q that basically measures how strong the negative part is. And I'm comparing like gradient descent for the overparametrized regime with 3 layers with the loss-enhancement algorithm. And then you can see, for example, when you have a Gaussian vector, like if the component is the magnitude of the negative component, it's quite small, like yeah, you can see that gradient descent performs better than the standard loss enhancement algorithm. And for the MNIST data set, I mean, you'll see next slide what I mean. So here we just took some digit from MNIST. We corrupted in 2 different ways, a lot of corruption, like a little less corruption, and then we compare the reconstruction. And as I said, since this is like everything around is 0, so when you corrupt, you have some negative entries, and then you try to recover it with a few measurements using that. So that's just a visual thing. So using loss enhancement algorithm and using the overparametrized gradient descent, and that's the difference. Again, like, is gradient descent better than a traditional approach? I would not say so, because a traditional approach means that like there is an explicit thing for that. So you want to solve a non-negative problem. That's it. While in our case, there's not like nothing explicit there saying like this is the algorithm is designed for this task. So yeah, you should have this in mind when you see this comparison. I mean, this is still work in progress. I mean, the paper will come in a few days, but I would say that's a summary of my talk. So, I mean, overparametrized methods are cool, and you have this bias induced by gradient descent. Somehow, magically, I don't know, we can solve a constraint least squares problem in an unconstrained way. Our approach is stable to negative perturbations. Because we are solving this in this unconstrained way, it has a lot of potential. I would argue for like scalable and accelerated solutions. And yeah, positivity or non-negativity is cool. Overparametrization as well. So I would say have a positive evening. That's it.
Question, comments?
Yeah, I'm wondering which class this is an image in. No, yeah, obviously non-negative
algorithms are important in lots of different fields in data science. I'm curious, because I'm not an expert in this at all, but like, is overparameterization an approach to non-negative matrix factorization?
Well, I would argue that's a natural extension. Maybe, yes, yes.
So this is something you're thinking about doing in the future, but not something that's like already kicking around.
No,
in
no,
the-
no,
in the
yeah, it's not
okay.
ready, but I would say that, yep.
Cool. Thanks.
Oh,
I'm curious, in one of your slides, you wrote that for Lawson and Hansen, there is no theory available. What did you mean by that?
I would say you have no, at least as far as I know, there are no convergence results or convergence rates, or like which are the correct assumptions for, but maybe I'm wrong.
Conversion of finite number of iterations.
Yes,
so
that's true. In
that's a convergence rate,
right. In the original book, they proved that. That's true.
But you cannot. So there is no. I agree with you. No way to bound in advance the number of iterations.
Right.
That it will
Yes.
take. And
Yes. Yes. Sure.
That's like, in my experience, this is a problem. So in the inner loop, you never know when you're gonna get out of it. And,
yes. Yes. Yes.
the number of iteration is finite, but can be
Yes.
very large.
Yes. Exactly.
And yeah, that to me is a big problem of the algorithm. I am optimistic that it can be solved, that the inner loop could be improved, but I have never found a way to do so. Another question. Yeah, so when the entries are, some of them are negative and small, have you looked at the implementation of Lawson and Hansen? Because it seemed to remember that there is a tolerance and that 0 is not really treated as 0 when they do
Really?
the test.
Okay, I need to check, because I must say I just played with it a lot, and yeah, things don't work well if you really perturb things. But I must say I need to check.
Okay.
Thank you.
Yeah, and there are also other things that could be improved in Lawson and Hansen that hasn't been improved in the MATLAB implementation, for example, and yeah, maybe somebody should do it.
Yeah, there are, I think, like 3 or 4 papers with some new ideas after their book, and these implementations, they work even better. I mean, you can find on GitHub. They are really good, but again, it's just some like heuristic thing. But I was playing with them recently, and they are really, really good, much better than the original Lawson and Hansen one.
Did you see an implementation of the following idea? Because at each iterations you solve the least square problems, but you never use the work that you've done before. However, the support, the active set is just increased by 1 index or decreased by 1 index. So if you keep a QR factorization that you update at every step, there is some potential to speed up the thing. Have you seen this idea being implemented?
That I showed in the beginning from this de Jong paper, I think it goes along these lines. So it's after their paper, there was another one based on their work that's doing something of this type. Yes,
okay.
yes,
Good
yes.
to know.
And this works much better empirically. Yes.
Okay, any other question? Okay, let's thank the speaker again. Don't forget that tomorrow we start 11:30 because we don't have lectures of Stefan. So you can sleep a little bit more. And Akran just landed, so he's in Toronto.
11:20, Carlos. Thank you very much.
No, you're welcome.
Yeah,
Thank you.
It's 11:20 tomorrow morning.
Okay.
Okay.